For this challenge, we thought of a few pain points that would inhibit the adoption and use of both CBDCs and public chains. For our entry, we have chosen to focus our solution on users and markets in the developing world because the unbanked stand to benefit most from this technology, as well as the majority of untapped natural resources being located there. The first roadblock is infrastructure, both in the form of reliable electrical power and data communications. Now, cellular service is available worldwide in a variety of service levels, but coverage can be extremely spotty, if not non-existent, in the majority of remote and undeveloped areas. This presents a serious problem for governments who intend to provide fair and equal access to digital currency to the entirety of its citizens, not just those located in the most developed areas of the capital. The installation of more cellular towers could be subsidized, but this vastly increases the cost and complexity of a CBDC rollout. For example, cellular towers in Africa can cost upwards of $250,000 per installation, and they still demand a reliable energy supply. What is needed is a cheap and license-free radio data network that can be installed and maintained for a fraction of the cost of traditional cellular data infrastructure. We propose to make use of off-the-shelf commercial and amateur voice transceivers as well as IoT LoRa devices to form an ad hoc peer-to-peer financial network. This network will consist of a few components such as the user access terminal based on low-power, single-board computers and ruggedized enclosures, as well as small freestanding towers or building-mounted Yagi beam antennas. Each node on this network will relay traffic to all other nodes it has contact with and forward that traffic to the nearest satellite ground station. Satellite internet is too expensive to deploy at any scale that would be useful for a national CBDC, both in terms of uplink equipment and data subscription charges. We propose to use our ad hoc radio data network to link terminals and villages so that a very small number of ground stations can be used to provide banking services to tens of thousands of users. Even more important is that by using VHF, UHF, and LoRa as the backhaul, it becomes possible to power this network entirely off solar power because of the limited duty cycles and the highly efficient nature of the network. We have developed specialized radio data network protocols that can turn low-cost commodity voice transceivers into secure and reliable point-to-point network interfaces. These new protocols bring TCP-like features and reliability to conventional voice radios, allowing for AES data encryption, forward error correction, over-the-air upgrades, and quality of service controls. The end result is a financial radio data network that can be deployed and maintained for a tiny fraction of the cost of traditional cellular data networks. Because our protocols run on a wide range of equipment, supply chain problems and the use of specialized or proprietary equipment can be avoided. Since all the equipment was chosen for low power consumption, large national networks can be rolled out rapidly without the requisite infrastructure required in traditional networks. Finally, we propose the use of specialized user interface terminals to allow payments both within a village and internationally without the need for smartphones or other expensive end-user equipment. By having a common and simplified user interface, people of all levels of technical competency can use CBDCs as easily as an ATM machine. So this is kind of a demo prototype. It is actually transacting on the XRP ledger with real XRP cryptocurrency using the radio sets and the protocols. Now the user interface is kind of a temporary construct. It was just built in order to facilitate the demo. Our next push will be on building a much nicer and friendlier user interface that would enable all the features of the XRPL. But for now, we're just going to go ahead and connect. So at this point, the network has completed the Diffie-Hellman key exchange and has initiated the AES encryption during the transport. And at this point, it's going to go ahead and just get the balance for the account that the terminal is using and then send that balance over to the machine via the VHF radio. So I'm going to go ahead and send 10 XRP from the terminal, and you can see the Zoom wallet underneath. It shows 9,000 XRP. So we're actually sending to that wallet through the radio network. So you will see the balance of that wallet actually get updated by the 10 additional XRP. So the transaction that was posted from the radio network has now been applied to the XRP ledger, and we'll see the balance on the wallet update by 10 XRP. So it's important to note that this is a full duplex time division multiple access protocol. So both nodes have an equal opportunity to speak. I've edited this out for time because we're only sending from one node to the other. Also, we're using Baofeng handheld transceivers. Those are pretty much the lowest quality equipment that we can find. So the protocols were designed to operate on pretty standard commodity commercial and amateur transceivers, so we can pretty much work with any radio that has a Vox circuit. And the host software itself is designed to run on either the ARM low power single board computers or on x86. So the protocol and node software is functionally complete, and we look forward to building a more complete and refined user interface on our next showing. Thank you for your attention.